co-author Harsa on this paper. So you should like definitely check it out, because this one is a short talk. So the main question that we ask in this paper is that, can we prove that the existence of one-way function is equivalent to the average case hardness of some NP-complete problem? This is an interesting question because it tries to base cryptography on complexity theoretic assumptions. So actually, what we will find out later is that this question is now answered by Liu and Paz, but in this paper we made some progress, and I will also explain how these two works relate to each other. So just some quick definitions about, okay, so what is a one-way function? It is a function that it is easy to compute it by with high probability over the choice of an input. It is hard to invert it. MKTP is this meta-complexity problem that appears in the title. So let's see what that means. So we need to define KT complexity. But what is KT complexity? It's like a variant of Kolmogorov complexity. So now let's see what is Kolmogorov complexity of a string. Okay, some definition, some like notation here. So basically, U is a UTM, D is a program, and basically what this notation says is that like what is the output of U if we run it for T steps on input Z. So this Kolmogorov complexity, basically we try to minimize the size of a program that computes each bit of the string X. So this is like a very standard definition. Okay. Now the notion of KT complexity is a computable variant of Kolmogorov complexity introduced some time ago, like in a work that also one of my co-authors is an author. And what we try to minimize here is the size of the program plus the amount of time that we need to generate each bit of a string X. So this is MKTP. It's basically a decision problem based on KT complexity. Now, this size parameter theta has some like reasonable upper bound here. It's not like arbitrary, but I'm not going to get into that. And basically, what we did in this paper is that we studied a notion of KT complexity that is conditional in the sense that you have some extra information Y. So when you try to generate the string, the bits of the string X, you also have this helpful information Y, apart from the program. And this is the decision problem that is about conditional KT complexity. So let's now see what we did with it. So what we did with it was to show that, okay, if there are one-way functions, this problem is average case hard. And if this problem is average case hard, then there exist one-way functions. And if there are one-way functions, then this problem is average case hard. But there is a catch here. Like this average case hardness in the second theorem is not very strong. It's like something like an inverse exponential hardness. So we just call it non-trivial hardness. Basically, what we wanted originally with this paper is to have an equivalence between the existence of one-way functions and the average case hardness of this problem. But this is something that we don't know how to do. Okay, so many years ago, like since many years ago, it was known that if subset sum is average case hard, then you can get one-way functions. So basically what we were trying to do is to solve also the other direction for one problem. And as I said earlier, like the problem that we started to solve, it is solved right now by Liu and Paz in a very nice paper that it is somehow like their story is tailored to our story. Because we published an earlier version of this work that had a bug inside But this inspired Liu and Paz to solve this problem that I mentioned in their paper. And the interesting thing is that we were also inspired to work on this by an earlier work of Liu and Paz, where they showed some equivalence of time-bounded Kolmogorov complexity. I mean, the average case hardness of computing time-bounded Kolmogorov complexity and the existence of one-way functions. So basically, we saw the paper, we started working on this question, we uploaded to ECC, there was a bug, and then they started also working on this, like to try to find an NP-complete problem that captures this hardness of one-way functions. And then we also, at the same time, like patched our paper. So it's like a give and take relationship. Also, like an interesting new paper is the one by Ren and Santanam, where they saw that MKTP, without the conditional here, is like the average case hardness of MKTP is equivalent to log space computable one-way functions. But like for MKTP, we don't know if it is NP-complete. Okay. Now that brings us to the other result that we have, that this nice problem is actually NP-complete, and there may be like some strong reductions here, like randomized and one-sided error. And another result that we have, which was inspired by Red and Santanam this time, is that log space computable one-way functions are equivalent to the average case hardness of MCKTP. Okay, but now I will not talk about this result here. Actually, I don't know how much time I have left, and if I have time to talk about techniques, maybe quickly. So, how much time do I have? How much?
2 minutes. 2 minutes.
2 minutes. 2 minutes. Okay. So actually, I will wrap it up because I don't want to delay a lot the next speaker. Okay, so basically, like this direction is about like so basically like we use this 2020 result by Liu and Paz, and we showed that we can get also one-way functions from the average case hardness of MCKTP, not just time-bounded Kolmogorov complexity. And the other direction is like more standard, is maybe a nice application of meta complexity. So basically, like you assume that you can solve MCKTP, and then by combining some maybe standard results, you refute the existence of one-way functions. And this gives like the contrapositive of what we wanted to prove. Now about the NP-completeness of MCKTP, just like we used like Ilango's work, like we adapted it, like in a nice way, I think. So open problems, it's just like one open problem. So like in this paper, okay, we tried to show an equivalence between like meta complexity and the existence of one-way functions. We did some progress, but Liu and Paz are the ones that actually solved it, to be honest. But like one question that is open is like, can we show such an equivalence for like other objects that are interesting for crypto, like public key crypto systems? And yeah, like many people helped us. Actually, Hanlin Ren and Mikito Nanasima found some bugs at some point in the paper. And like we had like really nice discussions with the rest of the people here. And thank you. Thank you very much.
Thanks, Dimitrios. Questions?
I hope actually, I hope it was not too fast.
So what are the ways in which your theorem falls short of completely answering the question that you began with?
Because like the quality of the average case hardness in one of the directions is not strong enough.
Yeah, and the problem, is it NP hard or only under randomized reductions?
Under this kind of reductions, like randomized, yes.
Randomized. Okay, I had another problem, another question after watching the recorded video, whether the question that you began with has been solved, but you answered it.
Yes, it is true. In a nice paper. So actually, Liu and Paz Now I'm like advertising also the work by UNPass. During the past year, they have written some very nice papers, almost all on the same topic, like around the same topic. And one of these solves this question that I mentioned. But they acknowledge in their paper that they were inspired by an earlier version of our work that had a bug. So I guess this is also some good credit for us.
Okay. Any other question?
Yeah, so you said that the problem of existence of one-way functions is equivalent to average case hardness of a problem. Is it known to follow from worst case hardness assumptions?
This is not known. I think that this is open. I don't think if something like that exists, but I think that this is something that it's like the biggest goal, like one of the biggest goals of complexity and cryptography, like to base the existence of one-way functions to the fact that we believe that P is different from NP, like to base it to the conjecture P is not equal to NP. So it is not known, like just average case hardness.
Right. I'm not an expert, but I've heard that there are some worst case to average case hardness reductions in crypto. I don't recall if it's for this particular problem.
Oh, I see. Actually, it is not okay. So, but they have to work for this particular problem, right?
Right.
Actually, right. Yeah, this is a good question. It's not clear to me if something like that applies to decision problems based on Kolmogorov complexity.
Okay.
Any other question? Okay, then thanks, Dimitrios.
Thank you very much.
And I'd like to call upon the next speaker, Ilya Volkovich. And I'd request you to start his presentation.
Hello. Hi, can I start?
Hello. Yes, please start.
So, hello everyone. Thank you for joining us virtually. I wish we could meet in person, but maybe, hopefully in the future. Nonetheless, in the meanwhile, let's try to be virtual. So I'm going to talk about approximating the number of prime factors given an oracle to an Euler function. That's a joint work with Yang Do. So basically, at a very high level, we're talking about integer factorization here. So I don't think I have to motivate this problem, but let me just remind that every number can be written as a product of powers of primes. And the algorithmic equation is actually to find those primes explicitly. And this is presumed to be a hard problem. In particular, the RSA crypto system strongly relies on that assumption. So if you want to do integer factorization, then if you want to look for an efficient algorithm, that's probably not something we want to do, but what we usually do in those kinds of cases when the problem is hard, we try to look at it when we're given some additional information. What if we have some additional information? So this is typically modeled by oracle functions. So assume that we have an oracle X of some interesting function. So what can we say then? So one such interesting oracle function, or function in general, is what's called Euler-Toten function. So it has a nice definition, which I suppose many of you know. If you don't know, this is a very useful function in combinatorics and other subfields, which kind of helps us. If you can see, it kind of tells us some story about the prime numbers. So the question is, what happens if I can actually compute this function, if I have an oracle access of the function? So this goes back to the seminal work of Gale and Miller, who showed that in this beautiful work, you can actually factor integers in polynomial time if you have oracle access to that function. So this was a very beautiful and seminal work, but it has one small asterisk, which is that the correctness of this result relies on the GRH. So that's a widely believed assumption, but it's still in the state of a conjecture. So if you use later Long and Rabin, actually remove this assumption and replace it with randomness. So you might have heard this story from a different angle. I believe many of you know about the Miller-Rabin primality test, but it's essentially the same story. In the same paper, Miller came up with a Miller primality test, which relied on the GRH, and Rabin improved this test by removing GRH and replacing it with the randomness. This is why I called Miller-Rabin, which is unconditional, which is exactly the same story. So then, since then, the next logical step is, okay, can we now also get rid of the randomness? Can we have a deterministic algorithm? There's been a work on that direction. So we don't know how to answer this question completely, but a few steps have been made. So specifically, Wall and Landau showed that you cannot compute, maybe not everything, but you can compute what's called the square free part of an integer if you have an access to this function. And there are subsequent or recent work by Zralik, Hittemeyer, and Tomekala that showed that you can get sub-exponential factorization algorithm if we have oracle access. And at the same time, very, very recently, Moran et al. Have shown that you can actually find a non-trivial factor of integers under some relative size condition. I'm actually going to mention that briefly. So there was some interesting development in this area recently, but the bottom line stays the same, which is we don't have polynomial time deterministic algorithm to factor integers, even if I give you oracle access to Phi-1, right? So basically, we're still in the case that we either need the GRH or we should use randomness. So that's kind of this question in this direction. Now, I wish I could give you a more satisfactory answer, but we're not there yet. So what is it that we know about it? So if we don't know the typical cases, if we don't know how to do a complete factorization, so let's try to take the route of Wall and Landau. Let's try to get some useful information. So what kind of useful information we're looking for here? So one such useful information is if I have n, I'm looking at the number of prime factors. So there are two versions of that. One is just the number k, the number of distant factors, and one is the big omega, which is the number of factors with multiplicity. So they're both kind of interesting ways. And in terms of what is known, so there's a almost, I would say, trivial upper bound. They're both of them are at most log n. At the same time, the only way that we know how to actually compute them is by factoring n. So there are surveys by Bach, Adelman, and Macaulay who say essentially claim that this is believed to be as hard as factoring n, because, well, we don't know any other way to do it, and probably the only way to do it is by factoring. Again, this is all kind of conjecture because we don't have any certainty here. It was recently that same work that I quoted earlier. They showed that when the number of factors is small, it's constant, you can actually factor n if you also have the prime factorization of Phi-n. So it also plays an interesting role here. Now, what we do know is that if the number of factors is exactly 2, like in the case of RSA, semi-prime, we can actually explicitly factor n given n and Phi-n. So this is actually a known result. So now, of course, the question is, can we at least compute omega of n, big or small omega of n, given oracle access to Phi? That's the question here. So can I compute the number of factors with multiplicity or without multiplicities deterministically given oracle access? So now this is the place when I wish I could give you a satisfactory answer to that, but unfortunately we're not there yet. But let me tell you what we know. So in this work, we make progress towards that. And what we show that we can approximate that number. So we show that there exists an efficient deterministic algorithm that given a number n outputs a number L, which satisfies the following. So the number L is between the actual number and 3 to that number. Basically, if the answer is k, you're going to get something which is between k and 3 to the k. So this is the main result. And again, that's an approximation result, which in my opinion, is still far from being satisfactory, but that's unfortunately the best thing that we know, given what we have. Let me just mention that it's still non-trivial when the number of factors is constant or even little of log n because of the trivial log n bound. And let me just also mention that it may seem that unsatisfactory, but at the same survey by Adelman and Macaulay, what they show that even deciding this problem, even deciding if L is fixed for L greater or equal to 3 is open. So basically, I give you a number and I ask you, does it have 3 prime factors or not? Very simple question. So even that is open, without the oracle, and even that is open with the oracle. So again, the only way to know we know how to answer this question is take n, factor n, and count the number of factors, which is again not something we want to do. We want to get better than that, but it's still open. So let me also remark that this approximation, it's not just for the little omega and the big omega, and can replace it for any what's called additive function. Doesn't matter what it is. If you know what it is, it's okay. So let me also mention that one of the things that we achieve while trying to prove it is an independent upper bound, which I think could be of interest, its own interest, something that connects the number of factors with phi of n. So what we show is that phi of n is at most this expression. You take the kth root of n minus 1 to the k. Okay. So this is in terms of results. How much time do I have to talk about techniques? 1 minute or less?
Less, so it's almost up.
Less, okay, yeah. But I mean, I did say the main result, but let me just mention that one interesting technique, which is this technique of Moran et al. So what they've shown is how you factor a number that has some relative size conditions. So let me just mention, because I think it's a very important piece here. So they define the relative size, which is the log of pi base n, and what they show is that if those exist, show that exhibit some weight conditions, if one beta is bigger than the other beta, so this is the relative size condition, then you can find a non-trivial factor. What we do here, we observe that you can actually extend it to something else. So if your number n has a factor which is smaller than n to the 1 to the 3 to the k, even k is being that, then you can actually extend this result to this case, because you can show that in this case, your beta would satisfy the largeness conditions. Okay. So if you want to see a more extended demo, I encourage you to watch the bigger version, the longer version. So let me just wrap up in here by saying that we give the first efficient deterministic algorithm that approximates the number of factors of an integer, both the multiplicity without the multiplicity version, if you have oracle access to phi of n. Of course, it would be nice to get a better approximation, but what we do here is that we actually try to directly compute this function rather than factoring n. First, we might end up factoring n eventually, but it's not the goal here. So this is kind of the new part here. And of course, the question is, can we improve the approximation, or can we get the exact value of omega giving oracle access to phi of n? And maybe can we get some other interesting function that we would like to compute about n? So one example would be the Mobius function. I think it's a very interesting question. Can we compute the Mobius function given oracle access? Because it will only be, if given our result, it will actually be to decide what the parity of this omega is. If you know what Mobius function looks like, so essentially you have to, it boils down to this parity, which we don't know how to do. So that's it, and thank you for listening.
Thanks, Ilya. Questions?
Sorry, can I ask one?
Yes.
Yeah. So just wanted to ask, you mentioned that in the previous surveys, it was shown that the complexity of computing Wn is at least as much as factoring. But then you said that your approach is directly computing Wn or omega n. So is it in some sense showing that these two problems complexity is different? Like computing omega n and factoring integers?
Just mention what I said. So Edelman and Corley had this survey, which I think it's a very insightful survey. They talk about the complexity of algebraic and arithmetic problems. So what they say, they don't show that that's equivalent. They kind of conjecture it very strongly. I mean, they say that they believe, and the same as there is another paper by Eric Bach. They say that it's widely believed. We believe that computing this is as hard as factoring n. This is why they believe it. In fact, the only way to do it is by factoring. There is no formal reduction. We don't, one-way reduction is easy, right? If you can factor n, you can compute omega of n. There is no known reduction that says if you can compute this, you can compute that. They don't know that. That would be a very, I think, interesting result to show something like that.
I agree with that. I just want to ask, since you directly approach the question of computing omega n, in some sense, is that an evidence that these two problems might have different complexity?
That's an interesting, I mean, that's an interesting thought. So, I mean, this is what we're trying to do, yes. So, but let me just mention that we try to compute omega n, but in some cases, our approach may actually yield the complete factorization of n. So, I mean, you may end up being in the case that you compute Wn because you kind of end up factoring. So, like, very roughly, the idea is what you're trying to do, like very briefly, if you want. It's here. So what you're essentially trying to do is you're essentially trying to run, there is this algorithm that can factor a number under a certain condition. So you try to factor a number. You either succeed or fail. If you succeed, you recurse on that algorithm. You take this d and d of n. If you fail, it actually tells you that the approximation that you have, the approximation by looking at this ratio between phi of n and n, then this ratio cannot be too bad, right? So that's kind of this two-pronged approach. You either succeed factoring, getting a factor, or you have a good approximation. So it's possible that every time you do it, you get a factor, and then you get all the factors. But it's also possible that, I mean, there are examples, we actually show examples in the paper when you end up, you actually don't factor, don't get any factor of the number, you just get the approximation.
I see. Thank you.
That makes
So also
sense?
the survey, sorry.
Yes, please.
Yeah, so the survey talks about, like, it does not talk about the problems with oracle access to phi n, right?
It mentions, so, I mean, they mention, so, okay, so they mention that, they mention a lot of things in different contexts, but specifically for the omega, they don't talk about computing omega with oracle, they talk about computing omega kind of, and it's as its own thing.
So this belief that these two problems have similar complexity, this is with oracle access to
I see your question. I see your question. That's an interesting question. So the belief that this is expressed in the several other works that I have quoted, Landau and Wall, it's so the survey, as far as I know, by Adelman and McCurley, they don't talk about those two, or they don't talk about omega in the context of oracle function. Other papers, they don't. Other papers, I'm trying to grab something concrete. Other papers, they talk about the relation, but
one more quick question. So does it
maybe
make sense?
That may be a good question. That may be a good question. I need to go back and see if this relationship is expressed, like the relationship is expressed without oracle kind of. Here is two problems. They probably like have the same complexity. In the presence of an oracle, that's, I don't think, I have to double check whether it's expressed that explicitly. That's a very good question. But
And
I mean,
does it make
the
sense to
goal is,
provide oracle access to some other function, like other than Euler-Toshed function? Does it make sense to study these questions with oracle access to some other function?
yes, so this is something that MRS did. So in their paper, they studied oracle access to Carmichael function, for example, or oracle access to the function which is the order of an element. So they actually did quite an interesting job studying the factorization with very oracle. So yes, I mean, it does make sense, and this has been done, but I should say, unfortunately, we don't have satisfactory progress. I mean, I wish I could say we have more things done, but this is, I think, a very interesting research area because of those, because we don't have, unfortunately, much progress on that.
Thanks.
I can
Ilya.
ask one more question.
Yeah.
So
Yeah.
I'm new to this. I don't know much about integer factorization, but so here you are approximating the number of this omega n, right? So I had a question that is there a approximate version for integer factorization also? Like, is there something that is there a problem which says that you approximate a factor by some amount? Output a factor. Output a factor.
Factorization?
Yeah, integer factorization. Yeah.
So,
like output.
Right. So you can talk about what's called incomplete factorization. So you can say, yeah, it's something you can define. You can say the holy grail is the complete factorization. I want to get some partial factorization. So in particular, was something that was done by Wall and Landau. They've said, well, you may not be able to get a complete factorization given phi of n. You may be able to get what's called the square free part. So what is square free part? So for example, if you take your integer, if you remove all the alpha i's, if you make them 1, you get what's called the square free or the radical. So this is something that they actually have shown that you can do. So given n and phi of n, you can deterministically compute the radical. So this, you can think about that as a partial factorization. Of course, you can say, okay, that's the natural thing. I can compute the radical. What else can I compute, right? So one of the questions, for example, this is, I think, a general question in factorization, and maybe somebody knows a better answer than I do. Is factoring radical, is factoring square free integers harder than factoring in general? There is this discussion about why, if you look at the RSA moduli, for example, they are radicals, they are square free. You have p times q, it's a special case. So is this any harder? Are those radicals, are those numbers which have square free parts, are those the hardest instances to factor? So this is one of the questions. In fact, Adelman and Macaulay, they asked that same question. Is it the case? Because if, for example, you know how to factor radicals using phi of n, and you plug in this result by Wall and Landau, you get it all the way, right? So that's another open question.
Right. Okay, thank you.
Did I answer your question?
Yeah. Thank you.
Okay, thanks, Ilya. The next speaker is Akhil Jalan. I request him to start his presentation.
Okay. All right. Can people see my screen?
Yes.
All right, great. Yeah, so hello everyone, my name is Akhil. I'll be presenting joint work with my advisor, Dana Mashkevitz, and this is on an explicit construction of expanding generating sets for abelian groups. So let's start with, So let's start with some definition or definition by picture. So this work is about Cayley graphs. These are graphs that are built from groups in a certain kind of way. And so in this picture, I've given an example where I have a group with generators A and B. And in this case, the vertices of the graph are just the group elements, and the edges are labeled by these generators. And so I can start from the identity element and then multiply by A and then multiply by A again, or I can multiply by B and then A and so on. And so this is a way of defining a graph which somehow captures the structure of the group. And expander graphs, I think we all know and love. An expander graph is just a graph with this combinatorial property such that sets expand outwards, and this is equivalent to a condition on its eigenvalues being separated. So in this image, I have a set of vertices in black and its boundaries in red, and the point is that the boundary is pretty large relative to the size of the set. So the motivation for this work is that expanding Cayley graphs, so graphs which have both of these structural properties, are a really useful pseudorandom object, and they're equivalent to many other kinds of objects that are studied in the literature. So one equivalent formulation is an epsilon biased set. This is, well, if I have fixed a finite field F, then I can define a Cayley graph on the group G, which is just the additive group of that field. And if this has spectral graph 1 minus epsilon, then this is equivalent to saying that the generating set S gives a pseudorandom generator against F linear functions. So in pseudorandomness, we're interested in de-randomizing various stronger and stronger models of computation. And so fooling linear functions is a very natural place to start. And it turns out that actually, even against low degree polynomials, the best pseudorandom generators we have are basically built by taking XORs of these pseudorandom generators against linear functions. Another equivalent formulation is epsilon balanced codes. So these are codes that are stronger than asymptotically good, because not only do they have strong minimum distance, but actually they have minimum distance almost as strong as possible, which is equivalent to every code word having roughly the same number of symbols out of all the symbols in the alphabet. And finally, these are also equivalent to objects which have sort of nice conditions on their Fourier spectrum. So these are all the same definitions, or their equivalent definitions, and this is the kind of object we're interested in constructing. And so some applications of this, for example, are low degree testing and an approach to matrix rigidity, which you can read about in our paper. So what can you do? Well, there is a randomized construction dating back to Allen and Reutemann, which says that if I take a finite group G and some desired epsilon, which will be the second eigenvalue of my graph, then just sampling a uniformly random subset of a certain size gives you the spectral gap that you want with high probability. And here, the number of elements you need in the generating set is n log G over epsilon squared. So we're taking it over G to the n, which means that this is roughly logarithmic in the overall size times this additional epsilon squared factor. And this is essentially optimal for abelian groups. So we know this is the target we want to aim for. So previous work de-randomized this with very suboptimal parameters for very specific groups, but none of them really came close. In particular, for the general setting of abelian groups, we get something like log of G plus n squared over epsilon squared all to the 5th power. So this is pretty far from this optimal size. Our result is that we can get an explicit construction deterministically in polynomial time. And we get parameters which almost match Allen and Reutemann. So the size of our generating set is n times polylog G times 1 over epsilon to the 2 plus little o of 1. So this is near optimal in the sense that it has the optimal dependence on n and almost optimal on epsilon. There is this polylog G factor, which we could hope to improve. But this is actually a byproduct of another construction we use. So it would have to, a work that improved this would have to go in a totally new direction. And let me just give you an outline of how we achieve this. So we start out with an initial set with poor expansion. So let's think of some generating set of G to the n, which gives a second eigenvalue on the Cayley graph that is less than 1, but very close, maybe 0.99. And in this case, we get that the size of the initial set is something like n times polylog G. There's also a very bad dependence on this initial expansion, but because this is a constant, that's not important asymptotically. The next thing we do is we use explicit constructions of expanders that are not Cayley graphs, but these will just be an input into our algorithm. And finally, we use an algorithm due to Tashma, which takes a random walk on what's called a wide replacement product of expanders. And the point of this is to amplify the spectral gap of this Cayley graph, which is very, very small, to a large spectral gap of 1 minus epsilon. And so because we can blow up the spectral gap, we get the overall construction we want, and we pay roughly a 1 over epsilon squared factor in the overall size because we do this amplification step. So the main thrust of our work is to analyze this algorithm that was already posed in Tashma in Stock 2017. So Tashma was studying the case of epsilon balance codes over F2, and we showed that actually this algorithm works for amplification on any abelian group. So I think I have 2 minutes. Let me try to give a flavor of why this is true. Essentially, if you take independent samples from your initial set, then you can show that the spectral gap shrinks very fast. The problem is that the size of your generating set also grows at that same rate, so there's no improvement in the epsilon dependence. One way of de-randomizing this is to take an expander walk. So instead of taking independent samples from your initial set, you can identify your initial set with the vertices of an expander graph and then take a random walk on that expander. So if you do this, then this is randomness efficient because now every step only takes log of the degree bits to specify instead of log of the size of the initial set. And so this gives you a significant improvement in the number of random bits you need, which is equivalent to the support size of the overall generating set. And the issue is that this falls short. You get an epsilon to the 4 instead of epsilon to the 2 dependence. So in order to get this epsilon to the 2 dependence, Tashma and actually even earlier work identified this structure called a replacement product. So this is a way of taking a product of the expander graph gamma, which corresponds to our initial set, with some inner graph H. Then you replace every vertex in gamma with a copy of H, and then you connect them according to the overall structure of gamma. And this somehow, if you choose the right H, gives you an even faster bias amplification or spectral gap amplification. So, okay, with 15 seconds, let me just say essentially the reason is because there's this technical barrier to the analysis of the ordinary expander graph, which is that you can get stuck in what's called parallel space. So this is the space of vectors who have eigenvalue 1 with respect to the graph. And the replacement product is a way of remedying this by using that information to show that you can shrink the spectral graph in a different way. And this is the same key idea that's used in Tashma's work, but actually also in an earlier work that gave a sort of version of the zigzag product, but for graphs with optimal spectral gap or Ramanujan graphs. And so the use of this wide replacement product is what allows us to avoid this technical shortfall, which means that we can show that the spectral gap shrinks very fast and get the overall dependence on epsilon that we want. Okay, so thank you.
Thanks, Akhil. Questions? Okay, thank you, Akhil. And yeah. So the next speaker is Jayakumar Radhakrishnan. I request him to start his presentation.
So Shagato, you can see my screen?
Yes, I can see your screen and hear you. You can start.
So, all right, thank you for coming to my talk. My name is Jayakumar Radhakrishnan, and I'm going to be talking about two coloring non-uniform hypergraphs. This is joint work with Aravind Srinivasan. So let me just introduce the standard terminology in connection with hypergraphs. So for us, a hypergraph has a vertex set, and it has a collection of, some subsets. These subsets are called edges or hyperedges. A uniform hypergraph is a hypergraph where all the edges have the same size. So we say that the hypergraph is R uniform if all the edges have exactly R vertices. And given a collection of such subsets, that is a hypergraph, we are interested in the problem of two coloring it. That is, we want to assign to the vertices colors red and blue in such a way that every edge receives both colors. So just as we two-color graphs, we can also try and two-color hypergraphs. The requirement is that every edge should receive both colors. Okay, so the problem of two-coloring hypergraphs is a very hard problem, unlike the corresponding problem for graphs. So it is NP hard even to determine if a given three-uniform hypergraph is two-colorable. Okay, so you're given a collection of subsets, and you want to know if you can two-color it, and that is an NP hard problem. It's also hard to approximate in the following sense. Amay Bhangale, recent result, showed that if you're given a four-uniform hypergraph, you're promised that it is two-colorable, but you're only required to find a coloring that colors it with these many colors, log n to the power some constant. And for some epsilon, if you can do this, that is, given a four-uniform, two-colorable hypergraph, if you can color it with these many colors, then that would imply that P equals NP. Okay. So in that sense, it's a hard problem even to approximate. Okay. So our discussion today is not about these complexity theoretic problems surrounding hypergraph two coloring, but it's more a combinatorial question. So let me describe it using a randomized algorithm, which one might try to two-color a hypergraph. That is, suppose you're given a hypergraph, you could assign every vertex red or blue independently. Okay, so if the number of vertices in an edge is large, then the chances are that some of them might receive red, some of them might receive blue. It's unlikely that all of them are the same color. And in fact, the probability that all the vertices receive the same color is this quantity for the edge F. And so the expected number of monochromatic edges will be this. Okay. Now, this already implies that if all these edges are large, then these probabilities are small. And if the number of terms in the sum is less than 2 to the k minus 1, then F is two-colored. So if you have few edges, then you can two-color an hypergraph by just randomly assigning colors red and blue to the vertices. So Erdős asked the following question. So suppose this expectation was not less than 1. Okay, so if this condition holds, then this expectation would be less than 1. But suppose this expectation was 5. So a random coloring, which is oblivious to the structure of the hypergraph, already colors all edges on average, except perhaps 5. Then is it true that any such graph is properly two-colorable, perhaps using another color? Okay. So I'm not sure I was very clear. So let me just read out what is written here. So let us just consider those hypergraphs which have at least k vertices in each edge. So each edge has at least k vertices. And let gk be the largest L such that every hypergraph F with this expectation less than L is two-colored. So suppose the answer for, say, 10 is true. That is, any hypergraph where the random coloring leaves less than 10 edges is also two-colorable using another coloring. Suppose this statement was true. Then we could ask, what about 11? What about 12? What about log k? What about square root k? So this function, the largest that you can promise, the largest value, L, such that if the oblivious coloring already leaves only L hyper edges monochromatic, then there exists a good coloring which would color all of them properly. That L is called G of k. Okay, so I hope the subsequent slides might make it clearer. Yeah, sorry, what have I done? Okay, yeah. So in 1978, Beck showed that actually G of k grows with k. That is, if the random coloring leaves log star k, only log star k edges monochromatic in a certain graph, that very hypergraph admits another coloring which perfectly colors it. And recent results have further improved this log star k to log k. Now, for special hypergraphs, hypergraphs that are simple, that is, where whenever two edges intersect, they intersect on only one vertex, there this G of k can grow, G of k grows at least as square root k there. Yeah? And in a previous work with Aravind, we showed that if we don't assume that the graph is simple, but if the graph is k uniform, that is, all the edges have exactly k vertices. The definition requires that all edges have at least k vertices, but if you insist that all edges should have exactly k vertices, then this log k can actually be replaced by a square root k. Instead of a logarithmic growth, you have something like a polynomial growth. And we know that the growth cannot be more than k squared. This is an old result of Erdős, shown using a probabilistic method, a randomly constructed hypergraph with certain parameters, and actually a k uniform hypergraph has this property that it has only the random coloring would only leave k-squared edges monochromatic, but nevertheless the graph has no two color. Okay. So what do we do? Yeah, so there is a gap between logarithmic growth when the graph is allowed to have edges of various sizes, all at least k, and it has polynomial growth when we assume k uniformity, and so there is a gap between these two things. And so what we try to answer or ask in this paper is that suppose we are told that whenever two edges intersect, actually it's enough for us if the intersections are restricted to one, intersecting edges don't have widely different sizes. Yeah, so one edge and the other edge, their sizes are bounded by a parameter lambda. Then, so suppose we restrict attention to such hypergraphs. So if it was k uniform, then this parameter lambda would be just 1. So can we prove something when lambda is 10, lambda is 20, or lambda grows a little bit? And our main result is that it's possible to extend the earlier results and show that g lambda k grows at least as this. Now, it's not very easy to understand what this function is, but let me just say that there is a parameter alpha which you need to maximize over, and then you have to take the minimum of these two things. So the minimum is over two quantities, and you have to find the best alpha, which maximizes the minimum of these two quantities, and that gives a lower bound on g lambda k. Okay. Now, in some special cases, let us say if you set lambda to be 10. So what is this? This is a hypergraph where every two intersecting edges have sizes which differ only by a factor at most 10. Then we get a polynomial growth. So we show that even if a random coloring leaves these many edges monochromatic, there is another coloring which would perfectly color the graph. And if lambda grows somewhat more than this constant 10, like square root log of k, then we can set alpha up suitably in this expression and extract such a lower bound on g. And this also grows faster than a logarithmic growth. So these improve the previous results under some assumption, and we will get improvements over previous results if we are allowed to assume that lambda is little of log k. So this is the main result, and we actually prove it using the method of Cherkashin and Kozik, which was used for uniform hypergraphs. And so we don't have any new algorithmic insight to contribute. It is the same algorithm. It turns out that the same algorithm, when run on hypergraphs where we have an assumption about lambda, where it will deliver a proper coloring with high probability. Now, so I'll just state this algorithm, and then depending on the time, I'll tell you in what way we differ from the earlier analysis. Is there any time?
You are past your time already, so maybe
I'm just okay. Yeah. So let me just say this. So if so the algorithm is the following: you just arrange the vertices in a random order and keep coloring the vertices red unless some edge threatens to become all red. Then you color the vertex blue. Okay. Now, this was the algorithm of Cherkashin and Kozik, and they had a certain analysis. Now, the main contribution of our paper is to show how that algorithm can be analyzed by tweaking one of the key parameters in their proof to derive our results. Okay, so let me just skip all the analysis and come to the conclusion. So this is what I already said, that we get some improvements over earlier results for certain values of lambda. The bound is constructive because there's a randomized greedy algorithm. And the interesting thing is that in my previous work with Arvind, we also had a randomized algorithm. And it turns out for a long time, we thought the two algorithms have roughly the same power. But it turns out that the work of Cherkashin and Kozik, the randomized algorithm, which I just described, which is very, very appealing, seems to be more powerful. it admits this sort of analysis that is there in the paper. But for the full problem, we don't have any improvement. The lower and upper bounds are still log k and k squared. Thank you.
Thanks, Jayakumar.
Yeah.
Questions?
So can I ask a question?
Yeah, please.
Yes.
So what do you believe is the true value of GK?
So actually, at the moment, even though we seem to be having difficulties in pinning down GK when the graph is not uniform. Yeah, if the graph is not uniform, we don't have a good bound. It looks like log k. All constructions are still with k uniform hypergraph. Okay. So I think whatever is the truth for k uniform hypergraphs is the truth for this problem as well. And what do we believe is the truth for k uniform hypergraphs? For k uniform hypergraphs, the lower bound looks like this, and the upper bound looks like this. And Erdős and Lovász in 1974, when in the paper which defined the Lovász local lemma, they conjectured that it should probably be k. So I would also think that the correct answer is probably k. And we are very far from it.
Thanks.
Is any better upper bound known for any interesting class of hypergraphs than order k square?
So actually, for example, if you know that the graph is simple, actually exponential. So if it is k uniform and the graph is simple, that is any two edges that intersect, they intersect in exactly one vertex, then you actually know that g of k grows at least as something like 2 to the k. If you know that all hypergraphs intersect at least in two vertices, then actually it turns out that such hypergraphs are always two colorable. That is, whenever edges intersect, they intersect in at least two vertices. Then I will let you figure out that such a graph always can be two colored.
So for which graphs did you say that GK grows exponentially?
K uniform and simple.
And simple. Okay. Thanks. More questions? Okay. Thank you. And let us thank all the speakers.
Thank all this. For the next session, we'll go back to the regular schedule. We won't delay the next session.
So it's from 4:45 p.m.
So basically, we only have 15-minute break after this session. Instead of 25 minutes, we'll start at.
It's just 2-3 minutes away.
Oh no!
So it's 5 minutes away.
Oh, am I mistaken? Wait a second.
5 minutes.
Wait. We had a 25-minute break, no?
We started late, perhaps.
Yeah, but the invited talk.
Yeah, I understand, but I thought we started 10 minutes after, and let me check.
So now it's 4:40 p.m. and it's scheduled at 4:45.
This session took 10 more minutes than allotted.
Yeah,
Sorry.
took slightly longer.
See.
Subsequence. This is a joint work with my advisor, Xin Li. Okay. So let me just briefly introduce the problem we studied. The first one is called edit distance. It's a very classical algorithm problem. So the edit distance is defined as a minimum number of insertions, deletions, or substitutions that is needed to transform a string X to another string Y. So for example, here, you can transform X to Y by delete the first G in the string X and replace the G with A, and finally delete the last, finally delete the last symbol G in X. So edit distance is 3. And another case study is called the longest common subsequence, also a very classical problem. It's ask us to output the length of the longest common subsequence. Like here, the LCS is marked in red. Okay. So let's review some classical results. So the textbook dynamic programming algorithm can solve both problems in quadratic time. And for edit distance, we know that if the edit distance is bounded by some parameter k, we can solve it by time n plus k squared. And we know that all these algorithms will need at least linear in worst case. Okay, and we can show some conditional lower bound for LCS and edit distance. For example, we can show that any truly subquadratic time algorithm would contradict the strong exponential time hypothesis. Okay, and recently there's a line of research on fast approximation algorithms for edit distance. And currently the best algorithm can achieve constant factor approximation of edit distance with near linear time. I mean, n to 1 plus epsilon for some very small constant epsilon. And all these algorithms are randomized. And the key idea of this progress sample and compute edit distance between pairs of substrings and the use of triangle inequality. Okay, so what about space complexity? The classical Stafford theorem tells us that any problem can be solved non-deterministically with space Fn, can also be solved deterministically with space Fn squared. So we know that both edit distance and LCS are in NL, and they can be solved with roughly log n squared bits of space in quasi-polynomial time. And for polynomial time algorithm, the best algorithm currently uses this only slightly sublinear, like this. And there's no truly sublinear space algorithm in polynomial time that is known. And the recent work shows that we can achieve very good approximation of edit distance and LCS with only polylog n bits of space in polynomial time. Okay, so like the title suggests, our work studies the streaming model. So what about the streaming model? So for the standard streaming model, we know that there are very strong lower bounds. Like for randomized algorithms, there's a linear lower bound for computing LCS and edit distance exactly. And for even for 2 over square root n approximation of LCS, we need at least linear space in a standard streaming model. And there's also very little, since there are strong lower bound, and for upper bound side, we know that if edit distance is bounded by a parameter k that is much smaller than n, then there exists some randomized algorithm that can compute edit distance in a streaming model with roughly k cube times Poisson space. Okay, and in our work we study a special model called a symmetric streaming model. This model assumes that we have streaming access to one of the string x and random access to the other string y. So you can imagine this scenario that when we want to compute the edit distance or LCS between y and many different string x, and we can assume that y is stored on a powerful server, and the computation is performed on some less powerful nodes. So this nodes has streaming access to one of the string x, and they can query y randomly by communicating with this powerful server. And our goal is to design a better algorithm or prove lower bounds for this model. Okay. So the asymmetric streaming model can be viewed as like an intermediate model between random access model and the 4A streaming model. It is first studied by Sachs and Sesh in a 2013 paper. In that paper, the authors give a 1 plus epsilon approximation of the algorithm for n minus LCS with roughly square root n space. And in a recent work, we can show that there exists 1 plus epsilon approximation
algorithm for both eddy distance and LCS in sort of n space. And also for the eddy distance, we can achieve constant approximation with roughly n2 delta space for any small constant delta. And for the lower bound side, there's no lower bound for eddy distance is known before in this model. And there's an omega n space or linear space lower bound for LCS when the alphabet is size has n from the lower bound for streaming long increasing subsequence. So in our work, we have proved lower bounds for both problem, and we also provided some improved algorithms. Oh, sorry, I just saw the message. Yeah, I'll go faster. So our work, so let me briefly introduce our results. So we first show that for randomized algorithm, if the alphabet is large, we can show a linear lower bound for exact computation. And for deterministic algorithms, we can show that for LCS, we need a linear space, even for binary strings. And we have proved similar lower bound for streaming longest increasing subsequence. Okay, and for on the result side, we improved the previous algorithm that require n2 delta space to d2 delta space, where d is the eddy distance. We also presented the half Prepson approximation for LCS with roughly n2 delta space. And the key idea of our proofs is using the communication complexity for lower bounds. So we always assume the local string y is fixed, and we assume the online string x is selected from some distribution. And we divide x into two or multiple blocks. Each party holds one block, and each party communicates with others to compute the eddy distance or LCS. Okay, so the lower bounds achieved from the communication complexity. Yeah. Since time is limited, I'll go to the algorithms. So for the algorithms, the key idea is that we, for previous algorithms, divide the string x into delta blocks. And our idea is to divide x according to the position of edit operations. Okay. Yeah, I think time is up, so I just stop now. Thanks.
Okay, thanks. Any questions? So what are the set of problems that you think these lower bound techniques will be applicable to?
Yes, I think this lower bound certainly holds for this our model called the symmetric streaming model. So like our techniques can also be expanded to show a slightly better lower bound for longest increasing subsequence in the standard streaming model. Yeah, and we have shown the lower bound for both exact computation and approximation.
Any other questions?
Yeah.
Okay, then thank you, Eugene. We can go to the next talk.
Okay, thanks.
In the interest of time, I think we can move to the third speaker because I don't have information about the second talk yet. We can start with the third one and come back to the second talk. The third speaker is Tanmay Inamdar, and the paper is ETH tight algorithms for geometric intersection graphs, now in polynomial space.
Can you see my screen? Hello?
Yeah, you can see it now.
Okay. Yes. So hi, I'm talking about our paper titled ETH-tight algorithms for geometric intersection graphs, now in polynomial space. And this is a joint work with Fedor Fomin, Petr Goluvac, and Saket Saurabh. So it is a very well-known fact that many graph problems admit sub-exponential time exact algorithms for many interesting graph problems like vertex cover, dominating set, Hamiltonian cycle. And the running time is 2 to the order square root n on these planar and H minor free graphs. And this follows from this well-known result that these graph classes admit order square root n size balanced separators. And this implies in particular that the tree width of these graph classes is square root n. And this type of running time is much better than the 2 to the order n running time for general graphs. And this is even tight as in ETH. So it's natural to wonder how far can this square root phenomenon extend? Like, can we get sub-exponential time for geometric intersection graphs? And note that these graph classes are not sparse, so they can contain arbitrarily large cliques. So geometric intersection graphs have vertices for every geometric object, and there is an edge between a pair of vertices if the corresponding geometric objects intersect. So if the geometric objects are very close to each other and if they all intersect, then they can form an arbitrarily large clique. So recently, Debug et al. Showed that in fact, this kind of running time is possible for the intersection graphs of similarly sized fat objects. So a fat object means that the ratio of radius between the in circle and the out circle of an object is bounded by some constant. And similarly sized means that the ratio of the radius of in circle of any object in the family is also bounded by constant. And if you have these kinds of objects in RD, then the running time is sub-exponential. It has this kind of running time. And if D is 2, then we get 2 to the order square root of n, like planar graphs. And this result they show by showing the existence of clique-based separators, and that implies the weighted tree width is bounded by square root of n. And they also show that this sort of running time is tight for these graph classes, assuming the exponential time hypothesis. And they obtain these algorithms by doing dynamic programming over tree decomposition. And this tree decomposition has this weighted width of which is sublinear. But one disadvantage is that the space requirement is also like bounded by this sub-exponential function. So it's natural to wonder, like, can we get the same tight running time, but improve the space to polynomial? So this is what we do. So we get the optimal running time for these family of graphs, but we improve the space requirement to polynomial. And to do this, we use the notion of weighted tree depth, which we introduced. And we get these results for like max weight independent set, vertex cover, dominating set, then like connectivity problems like feedback vertex set, Steiner tree, and like Hamiltonian cycle, and so on. So let me talk about the notion of tree depth. So here I have an example of a graph on the left, and on the right I have the tree depth decomposition. So tree depth decomposition is a pair of like forest F, which is rooted at some vertex, and this bijection phi. And this bijection satisfies the property that like if you have an edge between a pair of vertices in G, then they must have the corresponding vertices in F must have ancestor descendant relation. So here you have this edge between this purple and pink vertex. So they have this ancestor descendant relation. And then the tree depth, the depth of this decomposition F phi is just the depth of this forest. And then the tree depth of the graph will be the minimum depth over all tree depth decompositions. So our goal is to bound the weighted tree depth. So let's focus on D equal to 2 case. So in this case, Debug et al. Show that these geometric intersection graphs, they have order square root of n weighted tree width. And it also implies that if you can compute a constant approximation to tree width, then that's also square root of n. And from here, we can get an order square root of n weight separator back from the approximate tree decomposition. And this works as a constant approximation to the sublinear weight separator. So let's look at a picture here. So here we have this separator S, which is a constant factor approximation. And this has the property that the weight is bounded by some constant times square root of n. So this is a clique-based separator. So it can contain some number of cliques. And notice here that the number of vertices in this separator can be much larger than square root of n. But this weight is defined in such a way that if your optimal solution for your favorite graph problems, it has some nice intersection with any clique, then there are at most 2 to the order square root of n ways in which the optimal solution can intersect with this separator. And so we can enumerate these ways and then we recurse. So once you delete this separator, your graph breaks down into at most 2 graphs with 2n over 3 vertices. And again, this is a geometric intersection graphs. So it will have a sublinear weight separator and you can recurse. So this sort of algorithm will lead to this recursion. So we make 2 to the order square root of n recursive calls. And then we solve 2 subproblems of size 2n over 3. And you can show that this will lead to 2 to the order square root of n running time. So the main idea is that using this argument, we show that the weighted tree depth is bounded by order square root of n. And in fact, many interesting graph problems have this nice structured interaction with the cliques. And this we use to show that the number of recursive calls can be pruned. And this leads to this sub-exponential running time. And we are only enumerating intersections with the separator. And this leads to the fact that the space requirement is also polynomial. And for some problems, we build on the existing single exponential algorithms in terms of tree depth, these existing results. And for simple problems like independent sets, just a simple recursive algorithm works. Whereas for connectivity problems like Steiner tree, feedback vertex set, and so on, we need to use this cut and count technique. So I'll just leave with some open problems. So this cut and count technique, which I mentioned, it is inherently randomized because it uses this famous isolation lemma. So one open problem would be to de-randomize these algorithms just for these family of geometric intersection graphs. And we introduced this notion of weighted tree depth to get polynomial space. So can you find additional applications of this notion? So that's it.
Okay, thank you. Any questions?
So do
Can
you
I
have
ask a
time?
question? Yes.
Yeah, sure, go ahead.
So what is the weight of the tree depth? I didn't get the weight part.
Yes, so it is kind of defined in terms of these cliques. So like it is defined exactly in such a way that if your solution has can only pick constant many vertices from any clique, then the number of choices that you will have to enumerate is like 2 to the order square root of n. So I'm not providing the exact definition here, but you can find that in the the extended talk or the paper. But it's like defined in exactly such a way that the number of recursive calls can be bounded by this.
I see. Thanks.
So it's not immediately clear to me that that space goes down, but it's sort of okay that the way it's set up.
Right. So like consider independent set, for example. So you're only enumerating like how many ways can your separator can intersect with independent set. So it can only pick one vertex from every clique. So you'll just enumerate all the cliques and then you make a recursive call. So like if you look at the recursion tree, then you are only like enumerating partial solution one by one. So you only use polynomial space at every vertex of the recursion tree.
Nice. Okay. I have to see the definition more carefully. Thanks.
So in the original paper by Debug et al., there were a list of problems which they solved in sub-exponential time. So
Yes.
Is your technique applicable to all of them?
All of them except for connected dominating sets. So that's kind of a bit annoying because that's the only problem we could not adapt the technique. and it's for very like specific technical reasons. So there is in fact a single exponential algorithm in terms of tree depth, and you, like their technique, Debug et al. Technique also works for this problem. But somehow when you try to combine these two approaches, it does not work for connected dominating sets. So that's the only problem we could not get.
So does it fail in the dynamic programming step or somewhere else?
No. When we try to kind of combine the tree depth algorithm and this like approach of recursion and cut and count, that's where it fails. So they can do it using DP, but then the space is sub-exponential.
So we still have some time. Any other questions? So there is a question for you. What is the result for Steiner tree?
It's basically this, like sub-exponential time and polynomial space algorithm, but it's unweighted Steiner tree.
The unweighted means just the number of edges in the intersection graph?
Yes.
So you want to connect a sub-collection of geometric objects with as few edges in the intersection graph as possible.
You are given like the set of terminals and you want to connect them using.
Yeah, the terminals are there, some objects also.
Yes.
Do you get any progress for thin objects by using tree depth?
No. Because this separator theorem is kind of shown in this Debug et al. Paper. So we just use it to kind of construct the bounded tree depth also. So it does not work for thin objects.
Okay, so if there are no more questions, we can thank you, Tanmay, and we can go to the next talk. The next speaker is Kshitij Gajjar. Kshitij, can you please share your screen?
Yeah, just a second. Okay, can you see it?
Yes. So the next talk is on approximating the center ranking under Ulam.
Yeah, hi. So thanks for coming for the talk or for the conference. I'm Kshitij, and this is joint work with Diptarka and Agastya. So let me get started. Just a second. Yeah. Okay, so there is an election happening at the office, and there are 6 candidates, and there are 6 positions. So the only question is that which candidate gets which position. So here are the 6 positions: regional manager, assistant regional manager, assistant to the regional manager, head of sales, head accountant, and HR representative. Okay. And all these positions have a strict hierarchy, regional manager being the highest and HR representative being the lowest. Okay. So there are 6 candidates, and how do you fit them into these positions? So voter number 1 decides candidate 1 is fit for regional manager, 2 is for HR rep, 3 is for head of sales, and so on. Similarly, candidate number 2 has their own choice. And sorry, voter number 2. Similarly, you have voter number 3 and you have voter number 4. Okay. So you want to make one final selection, and you have all these different choices. So how do you do it? It is obviously impossible to satisfy all the voters because you can only make one choice at the end. So you want to somehow minimize the dissatisfaction of the voters. Okay, so what do we mean by this? So let's try a first attempt. Let's try to satisfy voter number 1. Okay. So we make the final selection exactly what voter number 1 wanted. And obviously voter number 1 is very happy. So what about voter number 2? Voter number 2 complains that I put candidate number 2 at the first position and you shifted him all the way to the last position. Similarly, for candidate number 2, I put him at, candidate number 6, I put him at the second last position and you shifted him to the second position. Okay. But after making these 2 changes, note that the permutation by voter number 2 is the same as the final permutation. So we say that the distance of voter number 2 from the final selection is equal to 2 because it required 2 moves to get from one permutation to the other. Okay, and formally this is called the Ulam distance. So Ulam distance is defined exclusively for permutations, and it is a minimum number of moves that you need to make to one permutation to get to the other. Okay. Now, in our scenario, we tried to satisfy voter number 1, and all the other voters were dissatisfied. And you can try this for other voters too. If you try to satisfy voter number 2, then 1, 3, and 4 will be dissatisfied, and so on. Okay. Now, the voters cannot complain in the sense that the final selection, they say that they are fine. Okay, maybe 1 move is required to get there, but 2 moves is too much. Okay. So can you have an optimal solution? And it turns out that in this case, the answer is yes. Okay. So if you take this as your final selection, then voter number 1 requires only 1 move to get to it. Similarly, voter number 2 also requires only 1 move. So does voter number 3 and also voter number 4. Okay. So in this case, the distance of all the voters is 1. Their maximum is also 1. So the highest dissatisfaction of the voters is as small as possible, because you can't have a distance of 0, obviously. Okay. So in this example, as you saw, that if you may try to select one of the given inputs, then you won't get an optimal, but you had to select a permutation that came out of nowhere and you got a solution. So this is what we are trying to solve in general. And such a permutation is called a center permutation. Okay. So this is a problem on permutations, but this has been studied for other metric spaces also. So if you're given a set of points in a metric space, then their center is a point that minimizes the maximum distance to all the points. Okay, to all the given points, and this is the formal definition. In our case, we are given m points. Okay. And the permutations are over n, and the measure of our distance is the Ulam metric, as I defined earlier. And the reason why this problem is difficult is because you can't check all the points in the metric space, because there are n factorial many permutations. Okay. And in fact, if the number of voters is fixed to be a constant, fixed to be 4, then we don't even know whether we can compute this in polynomial time, and we don't even know if it's NP-hard. Okay. However, if the number of voters is also part of the input, number of voters is m, then we know that the problem is NP-hard. Okay, so this brings me to our contribution. So we show that you can't find the exact Ulam center, but you can have a 1.5 approximation of it in this amount of time. In this, notice that if the number of given permutation, that is m, if m is a constant, then our algorithm runs in polynomial time. Okay. And if the number of given permutations is 3, then we can find it exactly. Okay. So 4 and higher, we still don't know what's the correct answer. Okay, so we provide a 1.5 approximation. So what about why 1.5? What if you need a 2 approximation? And this is easy. How is it easy? Okay. And yes, so none of you said anything, and that's correct. That's the right answer. This algorithm is just do nothing. You take the input set of permutations, and you do nothing. You just output one of the permutations. Okay. And the claim is this is a 2 approximation. Why? Let's assume P star is an optimal, which is not one of the given inputs. Okay. And P1 is what you outputted. Then since P star is optimal, this distance is at most opt. This distance is also at most opt for any other permutation. And by the triangle inequality, this is a 2 approximation. Okay. So why do we study the center? Okay, what is the point of studying the center of a given set of points? Okay, so suppose look at the following example. You're given a target to shoot at, but you're not an expert shooter. Okay, you're aiming for the bullseye every time, but in your first attempt you miss. In fact, you miss so badly you hit it completely outside the target. Okay, but now you know you were too high, so you recalibrate, and the next time you end up a bit too low. Okay, so you recalibrate again. And now you are from the vertical perspective, you're somewhere there, but not yet from the horizontal perspective. So you aim a bit to the right, then a bit to the left, and so on. Okay, you have a lot of attempts. And it turns out none of your targets actually hit the center of the bullseye, but they are all roughly around it. And the point is that now, even if the target is taken away and someone calculates the center of these points, it will be very close to what the actual bullseye was. Okay, so one of our applications is motivated by this bullseye example. The first one is what we already saw. In the second example, is speech recognition, where you're trying to speak something and the system is trying to recognize it. The first time you say a given word, then it will happen that it will match it to the closest word in the dictionary, but that need not be the word you tried. So you'll try to modify your speech or your accent. You'll get another word, then you recalibrate, and so on and so forth. And finally, the system gets this bunch of dictionary words and it tries to find the center of them, which is what you wanted it to. Another application is computational biology, where the DNA of one offspring is given. And in this case, you need to find two centers, one corresponding to the male parent and one corresponding to the female parent. Okay. So how much time do I have?
You have around 2 minutes.
Okay, yeah. So that's good. I have only 2 slides. So I'll just spend 2 slides on our algorithm. So it's a 2-phase algorithm. In the first one, so this is kind of what one does with linear programming. You can't solve the problem, so you relax the problem to a more generalized variant, and then you round up the solution. So in phase 1, we solve a generalized variant of the problem. So we view the permutations as strings, okay? A permutation is a very specific type of string in which each symbol occurs exactly once, okay? So we look at them as strings and we find their center. We can do this in polynomial time, okay? So we can find the center string optimally in polynomial time. That is phase 1. So let's look at an example. So these are your permutations. You find an optimal string, and this is a string, right? It's not a permutation, but it is a string. Now, if the string contains each symbol exactly once, then you're done because it is already a permutation. Otherwise, there are some symbols that occur multiple times or some symbols that are missing, okay? So in this case, the symbol A occurs twice. So you delete you delete the second occurrence of A and you insert C, which is the missing symbol, okay? Now, phase 2 can also be done optimally in polynomial time. And that is the weird part. So when you put these two algorithms together, although individually you can perform both of them optimally, the final result we get, we can only prove that it is a 1.5 approximation of them. Okay, so this is my last slide. So yeah, so how do you prove that this is a 1.5 approximation? So you need to compare it with something. And we compare our solution with the optimal center string, which we already have from phase 1, okay? Now consider a symbol which occurs multiple times. So suppose a symbol occurs 7 times, okay? Then for the center permutation, you need to delete 6 of the occurrences because you can only retain it once. In a permutation, each symbol should occur exactly once, right? So what we do, we just pick one of the occurrences uniformly at random, just randomly pick one of them with equal probability, okay? And we do this for each symbol that has multiple occurrences. So we create a permutation by this randomized process, okay? And it turns out that the permutation we obtain after this is a 1.5 approximation of the optimal center string. So the expected value is a 1.5 approximation. And there is a star over there because there's a small caveat that you need to apply a concentration bound at the end to get it up to that. But this is the basic idea behind it. Okay, so yeah, we have a couple of open problems and I'd like to stop here. Thank you.
Thank you. Any questions for Kshitij?
So is it FPT or something if say the optimum value is small, say if the optimum center radius is small?
Oh, we don't know actually.
I might be not.
No,
I guess it's not hard because n to the k is, yeah, what about FPT, I guess?
Yeah, so because we have m in the exponent, for small values, we just brute force. Because we are allowed to have, yeah.
Well, when n and m are large, but k, the radius is small. Maybe it's easy, I can't, yeah. Anyway, interesting open problem.
So what is known, if you don't allow one of deletion or insertion, what is known for that?
Sorry, if you don't allow?
If you, so here you're allowing both deletion and insertion of alphabets. Is it possible that you don't allow one of the operations and still you get some approximation?
Oh, then it won't be a permutation, right? It will be a string. So to get permutation, you have to both delete and insert. Was that your question?
Okay.
So one could claim that Ulam metric is a bit tough metric, no? In the sense, it's not, it's just counting the number of changes irrespective of how far you're moving them, right?
Yes, yes, that's right.
So I mean, in some sense, it's a tough, I mean, it's maybe, it's interesting, but it's a bit also maybe unnatural, right?
Yeah, also the reason like this, our algorithm, what we use is that this is the Ulam metric is exactly the opposite of LCS, longest common subsequence. So the Ulam distance between two permutations is always n minus their LCS. So the smaller the LCS, the greater the Ulam distance. And yeah, and that is kind of what we use for our algorithms also.
Okay, thank you. Yeah.
Okay, any other questions? Okay, then thank you, Kshitij. The next speaker is Diptarko Chakraborty.
Yeah, hi. So let me share my screen. So I hope you can now see my screen, right?
Yes, I can see it.
Okay.
So the next talk is Approximate Trace Reconstruction via Median String.
So thanks. This is a joint work with Devarati Das and Robi Krautkammer. So let me start by defining the trace reconstruction problem. So this problem is essentially a problem of reconstructing an unknown string from its noisy observable copies, which are also known as traces. So more specifically, suppose we are given an unknown string of, say, length n, but what we can observe is some of the noisy copies of it, say x1, x2 up to xm. And each of these noisy copies, we can refer to them as samples or traces. And then what type of noise, I will define that in the next slide. And the objective is to now recover that unknown string x from these samples. And what we want, so first of all, we want to use as few samples as possible. Second, we want to minimize the error while recovering x. And third, of course, we want the reconstruction procedure to be as efficient as possible. So now let me talk about what type of noise we consider. So here is this noise channel. So x, the unknown string, will pass through the noise channel and it will generate each of the traces. So now the most basic noise channel is the substitution channel, where each symbol is flipped with probability p. And this channel is not difficult to handle. And then the more difficult one is the deletion channel, where each symbol is deleted with probability p. And even more challenging one is the insertion deletion channel, where basically both insertion and deletion operations are allowed. And of course, one can also allow substitution, but for simplicity, we are not going to allow that throughout this talk. And also throughout this talk, we assume that insertion and deletion probability are same. So with 1 minus p probability, we will keep the symbol as it is. Then with probability p by 2, we delete the symbol. And with probability p by 2, we insert a uniformly random chosen symbol before processing the next symbol. And this is the channel what we will talk about throughout this talk. So now, in terms of the unknown string, also there are two cases for trace reconstruction problem. So the more general case is the worst case, where the unknown string is arbitrary. But a simpler one is the average case, where unknown string is an uniformly random chosen string. And as our title suggests, I mean, we will consider this average case version in our paper. Okay. So what are the applications? Actually, this problem has several applications in computational biology. But yeah, so I will not talk about application in detail. So one application that just I want to highlight is the DNA storage system, because this is an application where exactly the average case version of the trace reconstruction problem is considered. What is known for a trace reconstruction for the average case? Yeah, so I'll not talk about worst case from now on. So in the average case, the current based upper bound, I mean, for exact reconstruction is we need exponential in log to the 1/3 traces to reconstruct exactly. And the running time is almost linear into the 1 plus little of 1. On the other hand, the lower bound is log to the 5/2. This many traces are always necessary. And now you can see that there is a huge gap between the upper and lower bound, and it is an interesting open problem to close this gap. But I will not go into that direction. Instead, I will ask a different question that what about approximation? Because all these results are for exact trace reconstruction. But what about approximation? Because many application actually doesn't need exact reconstruction. For example, DNA storage system. For that particular application, even like approximate trace reconstruction will suffice. So what is the approximation here? So what we essentially want is that we want to recover a string, another string Z, that is close to the unknown string X. And there are different closeness measures that people consider, and that is defined over the string tree. So, but one natural one is the edit distance. And why this is natural? Because I mean, in the first talk, I mean, of this session, we have already seen the definition of the edit distance. And it just says that between two strings, what is the edit distance? It is the minimum number of insertion, deletion, or substitution operation that needs to transform one string into the another. And now from the definition, you can see that this distance measure is very natural with respect to this problem, because our noise channel also insert this edit noise. And that is the reason we consider edit distance as the closeness measure. Okay. So the question is, what can we do with approximation? Well, so one a very trivial observation is that since the noise rate is P, if we consider any of the trace, input trace, that is of distance roughly Pn. I mean, it is 1 plus epsilon times Pn, but say, let's ignore the 1 plus epsilon terms and consider it is just Pn. So it is almost of edit distance Pn. So the question is, can we do something non-trivial? Can we get something much better than Pn? So far, we don't know any such result. So what we prove in this paper is that only using 3 traces, we can construct a string Z, which is of edit distance from the unknown string, P square log 1 over P times n, which is much, much less than P. And also the running time is almost linear, O tilde n. And our algorithm is also deterministic. But I want to highlight the number of traces here, because if you recall in my earlier slide, I already mentioned that for exact reconstruction, we need at least a log to the 5/2 traces. But here, I mean, this is just a sharp contrast with the exact reconstruction. Here, just 3 traces suffices. And also, I mean, we consider binary alphabet. So somehow binary alphabet case is the most difficult case, because actually, if we allow slightly larger alphabet, something like poly 1 over P, I mean, if P is constant, this is just a large constant size alphabet, then we can even get rid of this extra log 1 over P factor from this term. And this P square n is essentially the best we can hope for using just 3 traces. Okay. So now, before going to the proof of result 1, so actually I will not discuss the proof of result 1, but let me now talk about a different problem, which is the median string problem. So in this problem, we are given a set of input strings, x1, x2, xm over some alphabet sigma. And the objective is to find another string y, which need not be from the input set S, that minimize the following objective value. So the objective value is the sum of edit distance to the input string. Okay, and if y star be a string that minimizes this objective value, then we call that string a median. So this median problem is a classic data aggregation problem, and it is defined over, one can define it over any metric space. And it has numerous applications depending on the underlying metric space. But I just defined it only over the edit distance. And also over the edit distance, it has several applications in computational biology. But I will not go into that direction because I want to show that how can I use this problem to show our result 1. So that is trace reconstruction problem.
Deeptarko, you have 1 minute left.
Okay, so I will soon wrap up. So yeah, so the median problem is NP hard, and there are exponential time algorithm for it, and it is also known that we cannot improve it by much assuming SCTH. But what about approximation? So in the approximate version, so if the optimum objective value is opt, then y bar is an approximate median if its objective value is at most c times the opt. And so the question is, can we get constant factor approximation in poly time? So the 2 approximation is easy actually. If you output the base input, then for any metric space, you can show that it is a 2-factor approximation. But what about pitas or even like breaking below 2? We don't know. But why I am talking about this problem? So for a long time, in practice, people are using this algorithm for median finding problem to solve the trace reconstruction problem. But so far, we don't know any such concrete connection between them. So what we have shown is that these 2 problems are essentially the same, at least in the average case. So suppose y bar is an 1 plus approximate median, then we show that this approximate median and the unknown string x are actually very close. It is of distance order epsilon by opt by m. And this is one of our main contribution in the paper, because if you could show result 2, then actually it implies result 1. Why? Because for each of the traces, for 3 traces, the optimum objective value, one can show that it is just 3pn. And now if you just replace optimum value by this 3pn and epsilon by p log 1 over p, then we get our result 1, the bound returning the result 1. The distance of y bar and x is p square log 1 over p. And for since I am using just 3 traces, one can use the standard dynamic programming, and it just takes cubic time. Yeah. So I will not go into the details that how we can improve this cubic time to the near linear time, and also how to prove result 2. So yeah, so if you are interested, you can talk to me later, or you can look into our paper. So now I will conclude by posting some open problem. So first of all, first open problem is, can we reduce the error by using more sample? Because everything what we have proved is for 3 samples, and that's why we get p square log 1 over p. So more specifically, we want to conjecture that the edit distance between the x and any approximate median could be reduced to epsilon n for arbitrarily small epsilon using more traces like poly 1 over epsilon traces, or maybe poly 1 over epsilon, or even poly 1 over p dependency will be there. And another open problem is that everything what we have shown is for average case. Can we show similar thing for worst case? Yeah, that's all, and thanks. So if you have any question.
Yeah, any questions? So what exactly happens when you take 2 samples?
If you have 2 samples, so then, so you want to ask that how can I reconstruct? I don't think we can reconstruct better than PN. Because PN we can always achieve because any of the trace will give PN bound. But if there are only 2 samples, I think with high priority, one can show that we will miss PN characters. I mean, we cannot reconstruct them better than PN.
And for your technique, can you go, I mean, do you get any improvement if you go to, let's say, 4 samples?
Yeah, so no, unfortunately, I mean, we don't know, actually. I hope that we can extend, but yeah, it needs more complication in the analysis. But I think one can extend, but yeah, we have not tried it, actually.
Any other questions? Okay, so I just, thank you, Diptarko. I just want to ask, is there any speaker here for the paper time-space optimal algorithm for computing separators in bounded genus graphs? Okay, then I think this brings us to the end of the session. Thank you to all the speakers and all the participants. When do we join? Yeah.
Yeah, I think we'll remind the audience about the invited talk at 7:30 p.m. Indian time of Leslie Goldberg. See you then.
Okay, so there is an invited talk at 7:30 p.m. IST. Leslie Goldberg will speak on approximately counting graph homomorphisms and retractions. Okay, are there any other announcements?
No, thank you.
Okay, thank you, everyone.